Okay, so this is one we started in class and didn't finish when we got stuck here, or that's where we ended up. So I'm going to go through it again. So this will seem familiar, but all the problems are the same, and they all have this given, this conditional probability. You can see it here when we have this in this question, and I guess I'll do this one after in a separate video. The one did not. This one has it, and this one has it. But I think the one with the newborns, no, it was kindergartners, and it didn't have that. So this beach wave one is, and by the way, you might not get the beach wave one, you'll get something else. So the way the person who generated this problem set is, not only can this question variate, meaning the numbers can change, but the question you would get in slot number 2 is like one of 4 different ones or something. And he's done that on all 4 of those. I think all 4 of the questions they're not going to be the same, which is good. It gives you a high number of practice to go through to be comfortable with these questions. So anyway, remember, if it's uniformly distributed, we're always going to be dealing with drawing a rectangle and calculating the area of the rectangle, because the area under the function, the horizontal line, down to the x-axis, that area represents the probability of selecting some successful outcome, what we define as success. In this case, the time the wave strikes within a given time period, an interval, which gives us an area. Today, the waves are crashing onto the beach every 4.7 seconds. The times from when a person arrives at the shoreline until a crashing wave is observed following a uniform distribution from 0 to 4.7 seconds. So in this case, I have a y-axis that I can see. That's my left boundary. And my right boundary is going to be at 4.7 seconds. So I'm just going to draw one here. It's completely arbitrary. So this is at 4.7 seconds. This is at 0 seconds. And then I have this function that governs the height. This function is f of x equals, and it's going to be some constant. If it was 7, it would be y equals 7, a horizontal line. This area has a probability of 1, because the probability of selecting a wave that crashed between 0 and 4.7 seconds is 100%, or 1. I'm going to erase these squiggles because I need space to write stuff and draw stuff. Okay. So before we even get going with this, with the questions that are being asked, let's set up or finish drawing our uniform distribution. I have to find that's not true. I understand the area of this rectangle is equal to 1. I need to determine the height of my function, or the value of my function, and I need this distance in order to do that. Why? Because the area of a rectangle is equal to base times height. This being the base and this being the height. Okay? We can determine the base because it goes from 0 to 4.7, so my base is actually 4.7 in length. And the height is, I don't know, so I'll just leave it as h. And my area is 1. Because the area of the rectangle, the probability, is 1. Dividing both sides by 4.7, I get the height of my rectangle to be 4.7. So this little 4.7 goes there. That's my height. And this base is equal to 4.7. I'm sorry, it's not 4.7, it's 1 over 4.7. Oh my goodness. Okay? So that's the first thing I do. I get the dimensions of my rectangle. Now I'm going to erase this stuff because we're going to need this space later. And it's redundant. Okay. Now, first question, the mean of the distribution is. So we have to calculate the mean. Because it goes from 0 to 4.7, I can tell you that the mean is going to be right in the middle, and we could simply divide 4.7 in half. But that's not always going to work. It's not the foolproof. It's always going to work that way. So the formula to calculate the mean of a uniform distribution is A plus B divided by 2. This left boundary is the value for A, and this right boundary is the value for B. So essentially, we're taking the average of those two numbers, 0 plus 4.7 divided by 2, and that's 4.7 divided by 2, which is 2.35. So this middle number, halfway between 0 and 4.7, is 2.35, which is our mean. So, boom. Okay? We won't need that information there. We'll need space, though. Standard deviation. The standard deviation for a uniform distribution is equal to the square root of b minus a, the quantity squared, divided by 12. You'll need to know that, or know where to find it. Remember, it's in the slides for this chapter, chapter 5. There they are, the mean and the standard deviation. So b, 4.7, minus a, 0, divided by 12. That's going to be the square root of 4.7 squared divided by 12. And we're going to have to put that in our calculator, which is the square root of 4.7 squared, all that divided by 12. And I get 1.356773133. Which, rounded to 4 decimal places, is 1.3568. And they do say 4 decimal places where possible, meaning you can. If you can't, because the answer is 1.5 or 2.35, then you don't go to 4 decimal places. The probability that the wave will crash onto the beach exactly 3.9 seconds after the person arrives is the probability of x equaling 3.9. And I'm hoping at this point in time, we do know that the probability of a single value is 0, because remember, we're talking about areas. So the probability of a single value is represented by a vertical line, and that line has no width. So that line, let's say that's 2.9. It's not, because 2.9 is over here somewhere, but whatever. 2.9, that can't have a probability because this line doesn't have any area, right? It's not two-dimensional. It's one-dimensional. It has one dimension from this here, from this point to that point. Or if it went on forever, it has infinite length in one direction, but it doesn't have another dimension. And so the probability of this is 0. If you have questions about that, again, the slide deck explains it, and I explained it twice during class. Some of you only got once, but that's that. It's on this slide. It says here, the probability of x equaling a constant, some value, is equal to 0. And they explain all of that sort of between here and here. Okay? Probability is found for intervals rather than for individual values for x. Why? The intervals will give us an area. This cannot give us an area. Okay? So that answer is 0. The probability that the wave will crash onto the beach between 0.6 and 1.8 seconds after the person arrives. And that's how we would write that. X is greater than 0.6, less than 1.8. So really we're talking about, okay, I didn't want to do that. Yep. Okay. So 1.8 and 0.6. So 0.6 is probably down here somewhere. And 1.8 is maybe here-ish. I'm just eyeballing to give us a picture. And so they're really asking if we want to know the probability of a wave crashing in between 0.40 and 4.7 as the time progresses that way. Like as soon as I walk to the top of the, stairs going down to the beach, if that's the kind of beach we're at, and somebody's down there looking at me, and I show up, they're waiting for a wave crash. They turn their head and look at the beach and wait for the wave to crash. They're averaging 0 to 4.7 seconds. It doesn't take longer than that. So they start the stopwatch as soon as I appear at the top of the stairs, and they swing their head over and wait for the wave. So if the wave hits right away, they'll click it. And we're trying to figure out what's the probability of the wave striking or crashing between 0.6 and 1.8. And so that is the area of that rectangle. See, now why is this erasing it out of order? That's just weird. Anyway, 0.6 and 1.8. Well, it really is just the area of this rectangle. So I need this distance here times this distance here. We know the height is 1 over 4.7. So base times height. We know the height is 1 over 4.7. We calculated that earlier. And we need this distance here, this length, if we wish, or the base, if you prefer. And we can just write down 1.8 minus 0.6, because that's that length. This distance is 1.8 minus 0.6. So 1.8 minus 0.6 is 1.2. I'm going to multiply that by 1 over 4.7, which is 1.2 divided by 4.7. And I get something like 1/4-ish, but it's not going to be exactly that. It's going to be a tiny bit more than 0.25. So 1.2 divided by 4.7, 0.2553. So this should be 0.2553. Just doing a little housekeeping. Okay, the next part of the problem. The probability that it will take longer than 2.54. So 2.54 is somewhere around here. And so longer would be anything over that way, right? But only up to 4.7, okay? So 2.54. Maybe 2.54 is not that far over, but it doesn't matter. We want to know the area of this rectangle, and so it's the same thing. Area equals the base times the height. In this case, the base is 4.7 minus 2.54. And then I'll multiply that times the height. The height hasn't changed. It's still 1 over 4.7. And so 4.7 minus 2.54 is 2.16 times 1 over 4.7, which is 2.16 divided by 4.7. I'm going to double check my subtraction. 4.7 minus 2.54 is 2.16. And I'm going to take that 2.16 and divide it by 4.7. And I get 0.45957, which is 0.4596. 0.4596. Okay. Again, we're still just no complications thus far, just calculating the area of the rectangles. I'm drawing the pictures so we can understand where these rectangles are, and I'm trying to approximate their size. I'm also telling you when that's not really exactly correct, but at least get an idea. Okay, so this one actually has to do with conditional probability. This is where we got started. I started to explain it, and I looked at the time and didn't think it was going to make it in terms of making it understandable in the amount of time we had left in class. So suppose that a person has already been standing at the shoreline for 0.7 seconds. Okay, so 0.7. Let's say that that's right about here. 0.7. Okay? So this time has already gone away. Okay? That time has already gone away. The wave has no opportunity to crash between 0 and 0.7. It has no opportunity because it has already gone away. Okay? So that time is gone. This is a conditional probability. Okay? We would write this like this. This is the probability of x being greater than some number, which I haven't read yet, given that x is already known to be greater than 0.7. Okay? So when we do either this question or I said the one above it, so we can do the one above it. So I said that already. We already know that this amount of time has gone by, so we already know that our x, the time, these seconds, has to be greater than 0.7. What that does is it changes the possibility, and we'll talk about how that works. Okay, so now the rest of this question says, without a wave crashing in, find the probability that it will take between 9.9 and 3.8. So the probability, the rectangle that we care about, is between 0.9 and 3.8. Okay, 0.9 and 3.8. So we want to know the area of this rectangle, but that's not all that we need to know. If we just wanted to know this probability, the probability that x is between 0.9 and 3.8, then we would simply calculate the area of this rectangle, and that's it. We'd be done. And so really this is between 0.9 and 3.8. But we still have this piece of information here, and I believe it's straightforward, but we'll see. So let's calculate this part first, which is the same as that. Okay, so I'm going to determine the length of this base, and we already know the height to be 4.7, right? Or 1 over 4.7. I keep saying that. I don't know why. So the probability of that is equal to the area of that rectangle. And so that's going to be base times height. And so that area is going to be 3.8 minus 0.9 times the height, which is 1 over 4.7, which is 2.9 divided by 4.7. And so 2.9 divided by 4.7. And I get 0.6170. I think that's what it said. 6170. Now, I'm not going to use that number, 0.6170. I'm going to use the number on my calculator because when I cut that off, it loses accuracy. Okay? So I'm probably just going to stick with this number, but I'm showing you if this is all we were looking for, that would be the answer. But it's not. Because I was told that it's going to be greater than 0.7, then we already know that this 0.7 is gone. This probability is no longer part of this whole giant or complete rectangle. This probability is now out of the truncated or cut off rectangle. It's this smaller one, the one that excludes this orange area. So really, I have to take this probability and divide it by the probability of, or in other words, this is equal to this green probability of 0.9, between 0.9 and 3.8. And that's divided by, I guess I used orange there, divided by the probability of x being greater than 0.7. So I'm going to use orange to keep my colors squared. X being greater than 0.7, that's equal to the base times the height. In this case, the base is 4.7 minus 0.7, this distance between this orange line and that one. So 4.7 minus 0.7 times the height, 1 over 4.7. And so that's 4 times 1 over 4.7, which is 4 divided by 4.7, which is like 90 or something like, maybe it's only like 80 something. 4 divided by 4.7. So 85%. So what I'm going to do is the following. Okay, this was 0.85, blah, blah, blah. Our probability, this one, is the probability that's going to be in here, knowing that my rectangle is smaller. So it's the probability of this green out of this rectangle, not including the orange part. Okay, actually I put a blue outline, maybe that'll be clearer. It's the green area divided by the area of my blue outline rectangle. The blue outline rectangle is this one. Okay? So my probability is this. For this little question inside our problem. Probability is equal to this green area, which was this, 2.9 divided by 4.7, divided by the orange, this, which is this one, 4 divided by 4.7. But notice, when dividing fractions, I hate this saying, but when dividing fractions, don't ask why, flip the second and multiply. That's the same as saying this. Keep, switch, flip. Wait, yeah. Keep, flip, switch. Or no, keep, switch, flip. Keep the first fraction, 2.9. I hate both of those sayings anyway. Switch the operation from division to multiplication and flip the orange fraction, the denominator. So it's 4.7 here divided by 4. And notice how these 4.7s equal 1, and I get 2.9 divided by 4. 2.9 divided by 4 is 72.5% or 0.725, and that's our answer. Okay? All right. Let's erase and get these last two. So the second to last one, 82% of the time. So this is the backwards one. When you hear me say backwards, it's because I think of this. It might not make sense to you, but after I explain this, maybe you'll understand. When you are in high school, you probably had to go take geometry, and you might have had like the area. Let's just stick with area of a rectangle. And so the area of a rectangle is base times height, and then it gave you like 3 and 1. And so 3 times 1 equals 3. The area is 3. Maybe I'll change that to 2, so this is 6, just so we have some numbers to play around with. Then they give you another rectangle, and they tell you the area is equal to 27, and they tell you that this length is 3. What's the area of this, the height? And so you have to do this, area equals base times height, but you're substituting 27 in for area, and 3 in for the base, and h. I call this the backwards area problem, because instead of giving you the base and the height and calculating the area, they're giving you the area, and you have to do some algebra to calculate the height. And it's not that big a deal when we're talking about area, or at least the area of a rectangle, because it's simple calculation. And you would just do that division. You probably wouldn't even write formulas down. But if it was like the volume of a cone or something, the volume of a cone is 1/3 pi r squared h. And so if I gave you the volume, 39 or whatever, and the radius is 0.7, you'd have to do some algebra to figure out what h is. That is what I call a backwards volume problem. So when I say backwards, it's just going in the opposite direction than what is the starting point, what you learned first. Because you learned how to calculate the area of a rectangle first before you started taking the area and calculating a missing dimension. Okay, so that's what this is doing. It's a backwards probability problem if you asked me to call it something. The reason why I call it that is because instead of calculating the probability like we've been doing, we are now going to find the value that's associated with a particular probability. So in other words, we're given the area, the probability, the 0.85, and we're trying to figure out the value that is associated with that, meaning this number here, or this number here, or that number there. Okay? Okay, so we're trying to sort out this question. Okay? It reads, 82% of the time, a person will wait at least how long before the wave crashes in? So they're standing there waiting, and 82% of the time, that means a large percentage of people, a large percentage of the occurrences will have to be waited for. How long will that be? Okay, so I'm going to change this question to try to help you sort out what's going on here. And I would never claim this to be easy, because I'm thinking about it, it's hard to explain, like painfully difficult for me to explain. There's an edit. You might spot the edit here. I don't know if it's going to be obvious, but I've done this. This is like the third time I tried to explain this, and it's not. I can perceive that it's not good. So I'm trying to do this another time. Maybe this one gets edited, I don't know, out. All right, so if it has, let's change this to 50%. And of course, that one's easy to spot, I hope. If you had to wait 50% of the time, someone has to wait how long? Well, that's going to be right in the middle, okay? And so we're really talking about, are we talking about this area or this area? And this is what I'm trying to explain by the way this thing is worded and why the answer is the answer that we want. And it's one rectangle versus the other. In this particular scenario, I say 50%. It doesn't matter because the answer is the same. But I'm going to try to use this to step to the next thought. Okay. So if I said 50% of the time, someone has to wait how long? Well, 50% of the time, people are going to hear a wave crash beforehand, and 50% of the time they're going to hear a wave crash afterwards. So for this one, again, it doesn't really matter because the answer is the same. It would be 2.35. But what are we talking about? When they say 82% of the time a person will have to wait, in this case, 50% of the time, someone will have to wait this amount of time. Okay? Now, let's change that 50% to some other number. And let's say it's 60% of the time. 60% of the time, someone has to wait how long? When I say 60% of the time, that means 60% of the people are waiting. That means there are more people that are waiting some certain amount of time before the wave crashes. We're talking about a line that's to the left here because this area is the 60%. Okay? This is the 60%. 60% of the time, someone has to wait how long? Well, they have to wait this long, and that's 60% of the people. This 40%, they are actually hearing the crash before those other 60%. Okay? Now, let's apply that 82% instead of 60%. Now we're talking about 82% of the people. 82% of the people have to wait how long? Well, 82% really means that I'm pushing this line to the left over to here. This is 82% of the people waiting this amount of time, this blue amount of time, before they hear a wave. 82% of the occurrences, the wave crashing, is happening after X amount of time goes by. And it's going to be a smaller amount of time, this 0.846, because they have to wait a shorter time for this larger percentage of people to get a wave. If I had said 20% of the time, someone has to wait how long? Well, 20% of the time is this little skinny over here. They're going to have to wait a lot longer. Okay? But the large majority of people only have to wait a short amount of time before they hear a wave. A large percent will have to wait a shorter amount of time for the wave to crash. A smaller percent have to wait a lot longer for a wave to crash. Now let's see if this calculates out correctly. If you calculate, we have to figure out what that is first. So 1 minus 0.82 is 0.18. So this is 18%. And so that's the area that I'm calculating, the base times the height. So we want to know this base, this little b, the height, of course, is 1 over 4.7. I think this explanation is the best one I've got, well, at least for now. I've explained it before. I don't know why it's so hard this year, but this semester, I don't know what's going on. And so now I have to multiply both sides by 4.7. This equals 1. I'm left with b. And over here I get 4.7 times 0.18. 4.7 times 0.18. And I get 0.846, which is the answer. Okay? 0.846. So that's the explanation I got. This last part, find the maximum for the lower quartile. Maximum for the lower quartile. So they're saying the maximum time for the lower quartile. The lower quartile occurs at quarter, 25%. So I'm doing the same backwards thing now, except I'm not messing around with that language. I'm being told 0.25. This area is 0.25. And so actually this last part of this problem is the easier of the last two parts. It's easier to do the one before. But I'm guessing that if the person put this above that, put this question above the G would be wrong every single time, because people would just do that math. So I'm going 2.5 equals base times height. Oops, that's mislabeled. We don't know what that is. Okay, 0.25 equals C minus 0 times the height, 1 over 4.7. 0.25 equals C over 4.7. Multiply both sides by 4.7. I know I'm going fast, but you can hit pause and or scrub and rewind, etc. That's equal to 1. I get C equals, and so that's 4.7 times 0.25. Well, a quarter of 4.7, which is 1.175. Okay? So maybe that helps. I'm going to have to end this, and then we'll start a second. It'll be a separate video to do this one above here. Okay? Hopefully those two will be enough.